Hello and welcome to the Nova Show. I'm your host, Chris Nova. Welcome to the show. Here at the Nova Show, we do what I want when I want because it's my fucking show. Welcome to the show, everyone. I was sitting here and I was thinking to myself. I don't know if y'all notice, I take a big deep breath before, like every time I hit the go button. And then it's this like very calming, like it just like hits you with silence. You're like, oh fuck, and then it's silent. And then you hit the button to start the show, and it's like dun da da da. And then I just stand here and I do nothing and just like hashtag exist during the intro, and I just like stand here very awkwardly for like 6 seconds, and it just feels like forever in my brain while like the music plays, and I'm like, okay, we just have to give the internet time to just observe me and perceive me, and then I'll be able to start talking. Anyway, how's it going? Welcome in, everybody. Welcome to the show. I hope you're all having a great day. I hope you're all having a great day today. How's the internet out there? Yesterday was hard. Yesterday was a hard day. For those of you who haven't heard, the main bank, the Silicon Valley Bank. Mute me now if you don't want to hear more about this. The Silicon Valley Bank closed yesterday. It closed. The bank shut the fuck down. The bank shut down. The bank in Silicon Valley. Like if you go to like Silicon Valley and you're looking for investor money and you are lucky enough to get a term sheet, or whatever term sheet you get the deal from the investors, and they say, we're going to invest in your little idea. And then the very next day you drive across fucking town, you go up the 101 and you go to Silicon Valley Bank and you say, hello, I'd like to open up a checking account with my $15 million, or however much money the investors are about to transfer to your checking account. And then if all goes well, you wake up and you have a Silicon Valley Bank checking account, just like the same checking account you or I have, with fucking millions and millions of fucking dollars in it. I've seen them. I've logged into them. I've literally logged into bank accounts with like $20 million in it in the startup scene. And every single fucking one of them was at Silicon Valley Bank. And that bank shut down on Friday. Welcome to the show. If anyone here is impacted, isn't sure if they're impacted, and wants to find out more, or just wants to talk through it, come to my Discord. We will help you. We'll help you get a job. We will help you find people to talk to. We will help you share news. We may not be able to do very much, but the one thing we certainly can always do is we can make sure you're not alone, and you at least have somebody to talk to about it. There's already people there who are going through it, and there's going to be more by the end of the show, I guarantee it. There's the people in the chat right now who you probably don't know who are joining the Discord right now. Who you could be joining and talking to as well. So the short answer is everybody's going to get their money. The question isn't if you're going to get your money. The question is when, and how much of it will you be subject to lose along the way. If you have $100 in the bank, you might get $20 today, and you might be given a few options. You can have the remaining $80 next year sometime, and you do a lot of paperwork to make that happen. Or you can maybe get another $10 next month, and we'll see how it goes, right? So everybody's going to get their money back no matter what. Nobody's going to really lose any money in these situations. You might like have to pay a lot of fees, and it might be very obnoxious, and people might end up going to like services, like private services that will take, you know, like how a realtor takes 7% of selling a house. There might be a private service that will help you with your money that will take 7% of your money, but they'll make your life way easier, and they'll say, you know, of your $100, we'll cut you a check for $90 today, and you just continue moving forward like nothing ever happened, and we'll take our 10%, and you don't have to worry about it. And that's going to sound pretty attractive to people, right? So everybody's going to get their money. The question is when and how much, and that's what's really happening right now. So anyway, that's like the implications. So what we're going to be doing today on the show is I'm happy to answer questions about SVB for a few more minutes. So if you have questions, put them in the chat. But today we're going to be looking at the Linux networking stack. Specifically, we're going to be writing a little bit of eBPF probe magic with Rust. We might write it in C. I don't know if I'm going to write it in C or Rust yet. It'll be one or the other. Maybe C. Maybe I'll write it in C. I don't know. If y'all want to see C or C Rust, just let me know which one you want, and we can do either one. And then we'll go into a lot of the detail about why we're doing it, what we're looking for, etc. And I'll even show y'all my new blog I'm getting ready to spin up. That's what we'll be working on today. So if you're new to the show, welcome. If you've been here before, welcome back. If you don't know what you are, welcome to the party. Many of us don't. I'm your host, Chris Nova. Welcome to the show. So for those of you who don't know, I am a kernel noob. I guess you can call me a kernel noob. I'm like medium low good at kernel things. Anyway, I'm going to be looking at trying to get some information out of the kernel that you can't really get any other way. There's a couple of ways to get it today, and actually that's going to be one of the things we talk through. But I'm going to be looking at getting specifically these things called accept queues out of the kernel, and we can go over what those are here in a moment. We're going to actually look at my blog and try to get my blog running as well. Okay. So anyway, hey Jay, how's it going? Welcome in, Jay. I might be asking you some questions about eBPF. So first things first, we're going to create a new repository for our work today. So this is going to be a repository for the Linux accept queues, and we can talk about exactly what those mean, because we will go to source, we will git clone, git at github.com, chrisnova.net.get, and then we'll move .net to chrisnova.net, and we'll make dev. And here's what we got. So I'm going to be bringing chrisnova.net online using GitHub pages here. Maybe today, maybe tomorrow, who knows? But until we get it online, we can just view it in localhost. Here's the new blog, and I have this one post. Did it not push? Let me push my code. 1 second. I've been working on my laptop, so let's see what we got here. I'm trying to open the Hacking Cap site, but it doesn't seem to work. Are you aware of the issue? I am. Thank you for asking. That's another thing that we need to fix this weekend. If anybody else asks about that in chat today, can y'all just help me and be like, we know it'll get fixed by the end of the week? If you need a link, we can probably give you one. You can just search for it on Lulu and share a link in the chat. So let me see. Get status, Goach themes, Hugo blog, awesome. Git save, and git branch, and we have main, and we'll do that, and we'll do git add star dash f git status, git save. There we go. So let's do a git pull now on my desktop, and we should get my changes. Cool. And we'll do an Emacs git ignore And we will do all of the ID stuff, which was just committed. And we will open up Sea Lion. And we'll go back to my terminal and we'll make dev. Make dev, and we'll go see what it looks like now. Still no post. Do I need to pull again? There it goes. And refresh. But it did not contain... Oh, okay, so change directory to... How do I want to do this? I need to... Git status. We'll say git checkout main. Git pull origin main. And then we'll do a git status. There we go. Git add, git commit sm, fix submodule. And now we can make dev. And there we go. Okay. Should work now. There we go. Linux accept queues. Okay, so this is what we're going to be talking about today. So I wrote this blog last night. Also, so Q, my partner, she picked out this theme, this Hugo theme for us. I fucking love this theme. Check out how cool this theme is. It's super simple. It makes me look smart, which is very rare for this fucked up person over here. But it makes me look like I actually know what I'm talking about, and that's very exciting. And so anyway, we have these things called Linux accept queues here. And the really cool part about this that I want to show y'all is, let me actually open up the website really quick. So we have Novix source, chrisnova.net. If you look at and I'll zoom in so you can see, if you go over here and you look at the content posts, you actually put the ASCII diagram in. This is text. This is ASCII text. And it uses this diagrammer called Goat. It's written in Go, the Go programming language. And Goat will take this ASCII diagram here, and it spits it out like it like formats it and makes it look all pretty, and you can like add colors, and there's like all kinds of cool stuff you can do with it. If you go and you look at like GitHub Goat diagram, you can see that there's like come on in, sweetie. You can see that there's like this whole set of diagrams and all these different cool things you can do with it. Anyway, that's Goat, and I'll let y'all just take a look at this while I tell my beautiful partner Q good morning. We're just getting started. I'm showing them the new theme that you just picked out. You want to tell people hi? Here. It's that camera up there.
I was like, it's one of these.
And then you want your face bar right here.
I mean, I'm actually going to say hi. I'm
say
just
hi.
Hanging out here.
I love you.
You smell like powder.
There you go. It's all the people from, like, Eska's here.
Yeah, it's Catterday.
Catterday.
I love this hoodie. Well, it's not really, it has no hood, but it's really soft. It's great. And it holds up in the laundry and stays soft, which is doubly great. Hello, hello. Oh, there's Preston.
Yeah, Preston's here. Hi, Preston.
And Gannett.
Hi, Gannett. See, all the people who like you come out of the woodwork. I was like talking about Linux accept queues and eBPF, and then all of a sudden you show up and everybody's like, "Oh, hi." Oh, do you want to?
He got gravied.
Will you tell the people what happened?
He got breakfast.
No.
Oh, so he got his summer shearing. He.
Please explain this, please.
Well, I mean, anyone who's had a fluffy dog understands that once the temperature starts to get past a certain point, his coat is just too warm for him. And so he gets shaved down a bit, partly so that it can start to grow back in, but also so that he doesn't overheat once the temperature gets past a certain point. Because he likes to run around, and like if he starts to slow down because he's getting too warm, it's time for the summer shave. Or at least round one of it. We keep him, he doesn't stay that short all summer. He's just, his first cut is that short. And then he gets maintained at maybe a couple inches longer than that.
He has been defloofed.
Yeah. Mm-hmm. And he has a bow tie now because bow ties are cool. Someone understood on the chat. I don't know who it is, but someone understood. Nova won't say it because she doesn't know why I want to make her say it, but that deprives the fun.
Say what?
Bow ties are cool.
Am I supposed to say those words?
I mean, like, it would help if you actually had the bow tie, but like...
Oh, I thought...
Bow tie has decided to take his bone into another room.
Got it. Okay, I'm probably gonna stream until...
Yeah, it knows.
I'm probably gonna stream until 12 or 1. Okay.
Yeah.
I'll do it after the stream. Okay.
Yeah.
Sure. Also, keep the washing machine open.
Okay.
It needs to dry out.
Yeah, sure.
Okay. Yeah, I'll do chores later this afternoon. Okay. I love you.
Actually, when I found that theme for you,
they can't hear you.
I don't need them to hear me. I'm talking to you.
It's like we.
Okay. I just, when you asked me to help you find a good theme that would render the things you wanted to render correctly, I also like your theme now more than I like the theme I'm currently running on my little blog that I don't advertise anywhere, so it doesn't get like tidal waved or anything. But I looked at this theme and I was like, I want this theme now.
Okay. I love you. Bye. Okay, and we're back. Okay, cool. So we have the goat ASCII art as SVG, and then I use ASCII flow, which is here, and ASCII flow will let you. It's like a diagrammer for ASCII, so you can add text. And, you could say, example text, and you can draw a box around it. And then you can, add arrows, and you can have the arrows go point to other boxes. And, it's a whole thing here. And, after you draw it, you can, move things around and, adjust them. And it's, really nice to be able to, basically edit, the things that you see in real time. And you can... even do freeform tools, which will allow you to do X's, so you can do X and you can change the character. It's a whole thing. So anyway, you get done with this and then you just copy, just Control C, and you just drop this right into one of these little goat doc blocks here. And this is how I'm going to do all the diagrams on my blog, and it'll get rendered in real time, and you can see this right here. I can even, look at the SVG if I want. This is the diagram that just came from ASCII flow. So it gives me an opportunity to really capture all of my work in my blog in something that you could realistically send as an HTTP request. Wow, that's insanely easy to use. Yeah. So this is how the source code looks. You can go and read the source code. I could show you my blog here, or I could show it to you here. Right? But it's straightforward. You could sit down as a human being and you could read this in Vim or Emacs or whatever, and it would be just as relevant. Right? So anyway, so we're going to be talking about these things called accept queues. I have a ton of nuance here and how they work, and there's an example of how to build a server in Go, and it talks about the trade-offs between Nginx and Apache. There's a ton of data here. I'm sure we'll go into all of it. There's even more data I could go through. So we're gonna skip ahead. We're gonna skip through all of this. And I think I'm going to go straight into this observing accept queues. Okay, so this is where we are today. We actually want to write some eBPF to help us observe these queues. And specifically, we're going to be looking for this magic queue length. We're going to be looking at for this value right here. Atomic TQL, QLen. the length of our queue. And we'll talk about these TCP fast open structures in the kernel and what they mean and why they exist, and we're gonna go deep into the networking stack today. So who here is familiar with the basics of the Linux networking stack? Raise your hand. Show of hands. One person puts their hand up. So anyway, it's gonna be fun. So that's how we're basically going to do it. So here's the question. We have a quick decision we need to make. Number one, do I push the blog to production and get the website online really quick so that folks can read the blog while I work? You see what I'm saying? Or do I just go straight into the Rust and just start working on eBPF and then push everything at the end? The reason I would want to do it now is because I suspect there are people out there who want to read the blog as it exists today. I guess if you really want to read the blog, I can just give you the GitHub link, since you can realistically read the source code, right? So let's see. Well, let's maybe just, I can share this, which I believe should, yeah, this is readable. You can go and you can see this today. So I actually think I can probably just do this. And there you go. If you want to go read about my work, you can just go and you can just read this little thing here. You can just read my work here. And so when we're looking at these accept queues, we can actually look at it here. We're going to be really talking about this FIFO queue. Oh, it's Hugo. Yeah, sorry if I didn't make that clear, Danielle. We're definitely running Hugo to render the blog. Okay. So let's get to it. We're gonna go straight into the Rust today. So the repository name for us is going to be, what do we want to call this? It's just going to be some like research in eBPF code to help us understand the accept queue len. So do we want to give it a fun name, or what do we want to call it? Like all eBPF probes, we could call it accept queue. We could call it net accept eBPF. We could just do it basically for all of the Linux networking. We could instrument sockets only. Let's just call it net eBPF. What do y'all think? Net BPF? Sure. We'll call it net BPF. Preston says, yeah. It has to be something with a Snoop if it's eBPF. So I'm not going to use BCC. We're gonna try to actually write this in Rust. So we could call it net Snoop, which I suspect that already exists. Let's go see. Open Snoop. Let's do Linux accept queues eBPF. I don't think I looked around. I didn't really see any of these. So there's the queue and stack maps. This is not what we're looking for. User API Linux. Yeah, no, these are different maps. IOU ring and eBPF. Yeah, see, there's nothing here, which is it's exciting because we found a use case we can instrument something with once and for fucking a while. And so anyway, I think we just call it net BPF. An eBPF probe used, we'll say this. Surface Linux networking metrics. We can't call it metrics. Events. We could call it Snoop Kit in honor of Boop Kit. What do y'all think? NetBPF or Snoop Kit? Some BPF love repo again. We'll make this in Apache too. I hate naming repos. We'll call it Snoop Kit, why not? Cool. We can always change the name later. All right, let's get it checked out. And actually we can go here and we'll go here. Git clone. Cool. All right, so we're gonna have to open up CLion. Is a legally distinct beagle. Well, somebody can pick a different name for me then. Somebody can pick totally not Snoopy. Somebody can pick a different name for me then. No, it's good. Okay. I just don't want to end up writing BCC in Rust. That's like the one thing I don't want to end up doing, but we'll check it out. So first things first, we're gonna create a new directory called. Let's do the architecture here. Snoop Kit reminds me of Snoop Dogg, looks fun. So I think we're gonna want to have a small C server that just calls listen, right? And never accepts. And we'll want to be able to curl the server to simulate an inbound connection or request. And we will want to report the accept queue length at runtime with eBPF. And so this report mechanism, I think, is basically going to be, there's going to be a user space program called Snoop Kit. And then there's going to be a single eBPF probe, which we have to, I don't even know where we're going to instrument. So we have to go figure out where we're going to instrument. Okay. I think that's what we're going to build. Does that seem like a viable starting point? And if so, maybe Jay, you know, is there a good starting point for a Rust eBPF layout? I guess I can just copy from Aura. I think I maybe should just use the one from Aura that we've been working on. I don't know if there's, look at Aya, says Jay. Okay, fuck yeah. Thank you, Rust eBPF. I just want I want the command line with like the arg parsing, and I want, are there examples here? Here we go. ILog macros. Here's an example. They have some archetypes even. I don't know what an archetype is. Here's a dev book. Development in a simple XDP program. So here, this is a good point. So there's like a template. Got it. Yeah. So we'll want to grab a template. So the question is, do we just want to actually just do some basic kernel hacking and just see? Let's just do that. Let's just write the shitty program and start curling it and see what we see and even figure out where we want to start instrumenting, because that's all going to be dependent on what we can see in the kernel. So let's actually do some kernel hacking. Let's like actually just start fucking tearing into my kernel and see what we can see. What do y'all think? Thank you for the sub, Taniwa. Thank you. So let's write our Nginx proxy analysis. Let's copy recursive verbose source into SnoopKit source. Okay. Yeah, let's build something so we have something to instrument first. Yeah. So here in the source directory, what I think we're going to actually do is we're going to move our source directory here to, we'll call this servers. So basically we're going to be simulating bad servers, bad sockets. So and we're going to have little C programs that can like do different things. We can call them servers, sockets, test cases, examples, workload generators. I don't know what to call them. We can just call it user space. I don't want to call it source. We can call them socket servers. We can rename it later. Sure, yeah. Okay, so we'll go into servers and we'll rmrf upstream. And we can go and we'll make our makefile here. Cool. So we have basic server TCP, and we're going to replace basic with healthy. I guess not healthy. Let's call it functional. We have functional server TCP, and we'll call this one the we'll do that. We can add exec to the end, so we can just remove everything with exec. Cool. So we'll copy this. And then we have to go and change each one of these manually. Server not accept Unix, functional server Unix. So we'll call this one dysfunctional. Did I spell dysfunctional right? I feel like it would yell at me if it was a typo. Oh, Linux Tips is rating with a party of 45. Thanks, Linux Tips. How's it going? Welcome to the Nova Show. I'm your host, Chris Nova. Welcome to the show. Dysfunctional with a Y. Dysfunctional. Listen not accept .c, and then we'll change this to dysfunctional listen not accept exec. Cool. So this one will be we'll copy this, we'll do that. Cool. And then we'll basically say this is server except not read unit. So this is just dysfunctional. except not read Unix exec. I feel like there's a way to automate the makefile here, but I'm okay with just doing these one at a time. Cool. Okay, so we should compile servers. So we should be able to now Emacs get ignore, and then we should be able to just ignore everything with exec in it, right? So let's make functional server tcp.c. Ah, yeah, I need to rename these files now. Okay, so let's go and do that manually. List. So we'll move basic server TCP to functional server TCP.c. We'll move basic server Unix to functional server Unix.c. And we'll move server except not read to dysfunctional except not read Unix.c. And we'll move server not accept to dysfunctional not listen not see, and then move server accept read not write read not write to dysfunctional except read not write Unix.c. And we'll move server except read not write close Unix.c. Of course, we're going to move that to dysfunctional except read write not close Unix.c. And a hole in one. And there you go. Okay, so and then now if I do a make clean. Ooh, what? Hold on one second. Let me close that. Let me open up a new terminal. Here we go. And we'll go to source, Snoop servers, Emacs makefile. Okay. So we want, where's our make clean? Cool. Make clean. And so our Unix one, so this is except read write not close. Except read write not close Unix. Okay, so arm dysfunctional except read write not close Unix. Make clean list and make clean and list, and there you go. Okay, and we'll save that. Oh, and I need to git add there, git status, and git save. There we go. Cool. All right, so we have our servers done. So let's now copy our server makefile here, and we'll Emacs this makefile, and let's see what we get. So here we're going to compile default compile, and so this will be compile servers. So we'll get rid of all of this, and we will say cd servers and make compile clean. We'll say cd servers and make clean, and then we can add our compile targets as we go. And so we'll make, then we should be able to servers, what do we have? Here we go. So if we run dysfunctional accept, not read. We'll say dysfunctional listen, not accept. Cool. So we're now running a dysfunctional server. So let's go look at the source code. I want to figure out where these little servers, their Unix domain socket is listening on. Okay, so we have listen not accept dot c. And where are, so we're going to replace this var run nginx.sock here. We are going to do a big replace where we replace this with var run Snoop kit server.sock. Okay, replace all. Replace. Chris, do you work with Rust? I'm new here. I do, yeah. We're just writing a little bit of C to get us started here. Just so we have something to test. And we want to basically be sure that we're going through glibc for these types of header files, because we're going to be exercising specifically their implementation of these tests. We'll probably also want to write some stuff in Go, because we all know that the Go programming language, of course, doesn't use any libc because they call system calls directly, which I'm not even mad. I'm just impressed. Okay, and so how do you curl a Unix domain socket server? That's the question. Oh, dash Unix socket. Okay, so let's try this. So let's run our address already in use. Var run clean. Do I need to make the file first? I always forget how Unix domain sockets work. You think I would have done enough for them in my life? Address already in use. Dysfunctional Linux not accept. Listen not accept. It's a socket stream. And then you bind it. Where's bind? To host adder. Socket Unix family AF Unix. Host adder socket Unix path sock. Which is here. Var run Snoop kit server sock. Why is this bind address already in use? Yes, aux grep dysfunctional. Cool. So why is this not working? Oh. There. We didn't have, the socket was owned as root, and that's why. Okay, I needed to run it as server. Okay, so cool. So now let's open up a client, and then we'll write some quick docs. And we should now be able to curl dash Unix socket. What was it? Var run Snoop kit server.sock. Yeah. I think you still basically do this. How do you, I want to see a, How do you curl a Unix domain socket? Does anybody know how to do this? Okay, I see. So you basically do curl Unix socket, HTTP / localhost, failed to connect localhost port 80. I guess index, why not? No, okay. So this is saying you can use SOCAT. Yeah, and people are basically doing... It's curl x... So this is saying you basically do curl... And you have to set the method. Failed to connect to index port 80 after could not... Forward incoming. So base plan is basically saying you create a reverse proxy. Missing a slash. No, the doc said that slash looked right. So forward incoming 8080 TCP to Unix socket using netcat. Make it via curl. So this is what I did in my Nginx proxy experiment. I basically used Nginx as a reverse proxy for this. I mean, we can also just, here, you know what, let's also do this. Let's do this. Fuck this. Fuck this noise. Fuck this noise. We are going to find our functional server TCP. We're going to copy this to dysfunctional. What did we call it? Listen, not accept TCP. And there we go. And then we'll just make this on port 8080. And we'll go to our for loop down here, and we will... Is the socket writable by your user? It is not, but that's why I tried to run curl with sudo. Okay, so let's do this again. And I just realized I have a bug here. Okay. So... Unix TCP.exec. So this one, and this will be dysfunctional listen not accept TCP.c. not accept TCP exec, and this is Unix. Okay, so let's go clean this up, and we'll move dysfunctional listen not accept .c to dysfunctional listen not accept Unix.c. And then we should be able to make, and we should have, there we go. And so now we have dysfunctional listen not accept TCP exec. And we should be able to sudo e address already in use. Is it because we didn't close the file descriptors? Let's rm rf bar run. You know what? Okay. So let's dysfunctional dysfunctional listen not accept TCP exec. Bind address already in use. Oh, it's because it's port 8080, that's why. Let's go here. Dysfunctional listen not accept let's pick a different port. We're going to do the old Nova port, 9074. And we will make and bang bang. Listen not accept Unix 1.c. Oh, did I put a typo? I did. There we go. Compile okay, and it's running. So I should now be able to curl HTTP localhost on 9074, and we should get a 200. And let's do a big -v. Perfect. We have one record in the queue. We can go instrument the kernel finally. Okay, finally. Cool. And we can clean all this code up, right? Like, you know, have it automatically manage the socket and stuff for us. I just don't want to get carried away. We have to go do all that junk with Aura, and I don't want to have to go redo all that again in my life. For now, this is fine. I can just hack it together. This is just a research project for right now. Okay. Basically, I just want to like prove this is something that is even viable to do, and if so, what are like the details around it? That's really all I'm trying to accomplish today. Okay, so let's kill our server, and we will make we'll make our servers again. We'll actually make clean, and we'll compile again, and then we will functional server TCP exec, which should also have a bad. Functional server TCP. This should also, yeah, 9074. Make. And then functional server TCP. And then now this should return a 200. And it does. And it closed our connection. Okay, so we have both. We have a functional server and we have a dysfunctional server. Written in C. So let's go up here, do source, Snoop kit, and we will git add, and we'll get save. Cool, and there we go. So now comes the fun part of today. Who wants to start digging into the kernel and see what the kernel has to say about all of this? So we will run our test again. This time we will make, and we will servers functional server tcp.exec. Open up the kernel, sudo open kernel, am I right? And we will rmrf var run Snoop. Address already in use. Org is listening on TCP. So this is fascinating. We didn't close the file descriptor in that bad server up here. We close new sock FD here, but we don't do it here. And the file descriptor is still open, so we're still bind is still bound. So now how do we clear the file descriptor there? On 9074, let's see. Nothing is. Why does it think it's still bound? You could look at LSOFF. List. Oh, I can never pronounce that command. All right, let's try this again. So this is functional server TCP exec. There it goes. That was working. I don't know why it wasn't before. Maybe I just had something outstanding. Okay, so now with Snoop kit, we want to run our curl silent v http localhost on port 9074. And that is our functional server. And now let's run our dysfunctional server. Listen, not accept TCP. Bind already in use. So why does this one? So many. Where's our bind statement here? Host adder. H to long. Port address family. inet. Adder is host adder. In adder any. What's internet adder any accept on any incoming messages. So that's basically 0.0.0.0. Any, yeah, says John. Yeah. So why does it think that 9074 buffer size? Listen not accept.c. So we'll say functional server TCP. Where's our host adder here? Bind host adder inadder any 9074. Bind address already in use. Do I need to make? I guess I just needed to recompile it again because it was probably just still compiled to 8080. I don't know why I did that, but anyway, I think it was trying to, maybe the binary was outdated or something. Okay, so here's our listen not accept, and this should be a bad curl. And there we go. Okay, so let's look in the kernel. So another thing I want to do, my menu bar started showing up here. Let's figure out how to get this menu bar to go away really quick. Where's settings? Is there like hotkeys? Terminal, advanced. It was on view menu. No, I know it's on view menu. I know you can toggle it here, but there was some hotkey that like, now every time I open a new one, it shows up and I have to come disable it. So like I did some like, is it like Control M? Let's go look and see. Cool retro term. Shortcuts, keyboard mappings. Alt P. I mean, I know I can, I guess I'll just turn it off. I don't know. It was on view menu. Right, but like I just basically, there's show menu bar. And now every time I open this up, I was like typing and I hit something and it toggled the menu bar and now it shows up every time and I can't get it to go away. And there's nothing in settings for like hotkeys, shortcut keys. There's profiles, there's help, edit, quit. Yeah, I don't know. Anyway, let's look in the kernel. Okay, so when I look in the kernel, I'm gonna go to sysfs, we'll go to BPF. We'll go, sorry, sysfs, oh my, what am I doing? Syskernel. Okay, so we go to the syskernel directory, and then there's a trace events in here. We'll start there. So tracing, this is a directory, if you're going to be doing kernel instrumentation, you should probably familiarize yourself with. But we'll go to events, and these are the different trace points in the kernel. There's a lot in here. There's a lot in here. So let's try to find the one we're looking for. So the one we're looking for is we want socket data. And we're doing a TCP socket stream server. There's a lot in there. Might need to do a strace. Does strace use those endpoints? These are other things outside of strace. This is like where we're going. We don't need strace. So these exist outside of strace. Well, some of them do. Some of them overlap one-to-one. But for the most part, these are all parts of the kernel that we can see that you wouldn't have observability into otherwise. If you wanted to basically replicate strace, you just use this one, known as system calls. But as you can see, there's a whole lot of other things going on. So the one we're going to be looking for, I bet it's in net, if I had to guess. So the part of the kernel we're looking in is basically going to be the network stack. In fact, didn't I check out? See how I opened up a new terminal and look at, and now this menu is there. See, this shit fucking drives me nuts, you guys. Is this like a cinnamon? Let's see, shortcuts, keyboard. Let's go see. Is there shortcuts here? There's Windows. There's toggle. Is there like a toggle menu? Before it saves its config. So you're saying I need to like close this one and then open up a new one? There you go. That worked. Thank you, whoever suggested that. That worked. Okay. Sudo e bash change directory to syskernel tracing. And then we want to go to events, and here we go. Okay. So socket, this actually might be where it is, the socket buffer. Anyway, so what we want to do is we want to open up a new tab, and we're going to go to source, and we're going to go to Linux, and we're going to get remote -v, and we're going to get poll origin main. Get remote. Oh, it's Linux. It's still called master. There we go. Okay. So we'll be able to look at the Linux source tree here if we need anything, but basically, we're going to be looking in this include directory. This include directory is what most people call the Linux kernel headers. And we can check out a tag if we want, but for right, yeah, let's check out a tag. Let's be thorough. Okay, so we'll say get checkout tag. I always forget how to do this. Let's see, we want to go here to our tags, and we're going to check out v62. So I think we basically can go here. We can go get checkout v6.2. Oh, sorry. Get checkout B, or get switch B. Hold on. V6.2. There we go. Get branch, get poll or origin v6.2. There we go. And so now we go into include, and then which kernel am I running? Okay, I'm on 6.2.2. That's close enough. So we'll go into include or include. So this is the Linux headers is what most people call them. So we're going to be looking in the Linux network stack, which of course is Who can guess where the Linux network stack lives in this directory? I'll give you a hint. It's here in this folder called net. And if you go to this net, they usually try to, we usually try to keep them as one-to-one as possible. So if one part of the kernel is called net, the 3-character net string, that usually corresponds to like what we see here. Net link, however, is a different part of the kernel, a little bit lower in the network stack than net itself. And we can, of course, we can go look at netlink, but I think we're going to start here at net, which is the highest level one. And so we're going to go directly into net, and we're just going to look at the Linux networking stack. And so probably the easiest thing to do here is just to check and see what's available. Just look and see what we got. No big deal, right? Just herpy derpy. This whole, everything we're looking at right now is known as Linux trace points. And you can easily turn them on and off just by echoing 0 and 1 to this enable file. So you can echo 1 to enable here. And if you want to actually see what's happening, and we're gonna look inside the kernel. Y'all ready for this? Oh, I need like some better music. We need like kernel hacker music. Hold on. I got this. Before we start to look at the kernel, wait for it. Just fucking wait, everyone. Everybody calm down. I thought I had beats. Here it is. And go. This will be a little bit more chill. Cool. Okay, cool. So it's about to go down. So we echo 1 to enable. And then there's this file in sys kernel tracing. There's this trace pipe. It's a Linux pipe file. It's a special file type. It's like the same way we can have device files that are special files. We also have trace files now because of the sys file system. Sys introduces these new file types called trace files. And this one specifically is called trace pipe. It works like a pipe. So what you do is you do what you do with all pipe files, and you can go and you cat sys kernel tracing trace pipe. And there you go. Welcome to my kernel. And if you don't believe me, you can echo 0 to enable, and we'll run our trace pipe again, and it stopped. Right? So we can look at all of these wonderful trace points in the kernel. And so when people are like, is this like strace? I'm like, kind of, but it's a little bit more exciting. At least it certainly can be. So what we're doing, what's up nerds? How's everyone? We are having the most nerd time right now. This is one of the nerdiest streams we've done on my Nova show. So what we're doing right now is we're actually looking at Nerd++. Yeah, we're looking at all of these events. And so if you really want to see what's going on in the kernel, I can tell you right now, the kernel's going to process several orders of magnitude more events than my little standard out can keep up with. Okay, and so we can look and see what's going on in the kernel, but as somebody who has instrumented the kernel in large distributed systems in the past, I'm telling you guys, it's a bad idea. There's millions of events happening in the kernel every second. Poof. A single compute cycle, I don't think folks usually understand how fast a compute cycle, like a single rotation, a single cycle of a processor actually is. I mean, we're talking millions per second. It's at a different scale. It's like the difference between like a microscopic scale and a macroscopic scale. It's like the difference between like driving across the street and going to the moon. It's just a different fucking country, different fucking planet. Like, it is two different things. So when we start looking into the kernel and what it's doing, like it's not like it's like you can just go tail a file, right? It is millions and millions of events per second, and there are several genius level folks out there who have dedicated their lives and their life's work to like giving us what we have right now so we can actually go and see this, and we are very grateful for them. So like, to give you an example, of what we're actually seeing in the kernel. And this is definitely not every CPU cycle in the kernel. This is every event in the kernel, which, you know, there's maybe one event per, like, you know, a few 100,000 compute cycles or something. So if you were to turn on all of the trace point events, which we're back in this highest level directory right now, and each one of these directories has like subdirectories, and in some cases it's like 2, 3, or 4 layers down. Like, for example, TCP has some trace points, but then you go into like TCP probe, and that has its own trace point as well, right? And so you can see there's quite a few of these. So if we turned them all on, every single one of them, and we ran our cat command, you can see we can get every event out of the kernel. And I can tell you guys right now that we're actually substantially delayed. And every moment we continue to run this, we're more and more and more and more delayed. We're more delayed. It's if you can see 2 lines on a graph, we're slowly dragging behind what's actually happening in my kernel versus what we're actually seeing on the screen. And one of the things you could do is you could like actually zoom out and try to get like more into my buffer here, and you would still see that it's extremely fast. For standard out, it's fast, but we're still too slow. Just doing this simple exercise of seeing everything, it's still too slow. We're still lagging behind the kernel. Well, there's not guaranteed to lag behind the kernel, but there's a high likelihood we are. And if we zoomed all the way out and we ran everything as fast as we could, these are all of the events happening in my machine right now. And it still is nowhere near the level of visibility you need. So you have to get smart. So you have to get smart with how you're doing it. And so we'll echo 0 to enable. Well, the timer goes up by about 1 per second, and that looks not really delayed. It's one of those things where it's like, it depends on like how busy your system is. I think I've just learned to never trust standard out is kind of what I'm getting at here. So yeah, there's a good chance that it's actually echoing out as fast as it's coming out of the kernel. And of course, each one is like liable to have its own latency. So yeah. Prismatic Martian says, it's awesome that you're showing this to us live on Twitch. Meanwhile, some power station on the other side of the world is shutting down and they have no clue why. Yeah. Except for like, I'm just looking at my computer. I'm literally just talking about like an old, like 10-year-old computer sitting on my desk. And something like grep keep up. Yeah, so grep and rip grep is all fine. So let me maybe frame this a different way. So Compile Nix brought up a really great point here. And let me just double down on Compile Nix's point and just say the following. The Linux engineers and authors would not have given us a file to look at with cat if they didn't believe there was going to be meaningful data coming out of the file, right? So like this whole infrastructure exists because like it is meaningful for folks like you and me to actually use command line tools to look at it, right? But there are certainly problems with it. And what I'm trying to get folks to understand isn't that like one way is good or bad or impossible. I'm trying to get folks to understand that like this is not, we're operating like in a different fucking dimension here. This is not normal compute world. We're working with the kernel now, and the rules of the game are different, right? It's computers on expert mode because we're now interfacing with the hardware and everything is event based instead of everything being linear and procedural like you see in Python or Bash or Ruby or any of these other like single threaded or even multi-threaded procedural programming languages, right? The kernel is, it's all, you get what you get, and sometimes you get double and sometimes you get triple, and memory is weird and it's all virtualized, and it's very strange, but it's very exciting, but like very strange. It's just a different world. Okay, but yeah, these files wouldn't exist if it wasn't useful for folks like us to go and look at them and use them. So I don't want you to think that these files are pointless. I found Tmux did some clever buffering that causes less for the terminal to render process. That's exciting. We were talking about the different like types of strategies you can use in user space when you're dealing with the kernel and how to do things faster. And I think there's still quite a bit of work to do in user space with everything from terminal buffering to request processing to, I mean, there's lifetimes of work to do there. Is there a special kernel thread to gather events and aggregate them to the pipe? Kind of. So we're looking at the Linux trace point subsystem, if you even want to call it that. Is it tracing? It's called kernel tracing. Here you go. So it's trace. It's monitor variable access, command usage, and executions. I think this is it. We might have to go and actually find a different man page. Let's see. Linux tracing man. Let's do trace points. There's event tracing. Here you go. This is what we're doing. Hold on. So this is from 5.0. So you can see this is a little more involved than what we're doing today, but this is a great resource. Let me share. So there's not necessarily a kernel thread, as much as we've just kind of built in this instrumentation into the kernel already using this, what did this call it? Event tracing set of features in the kernel. And there's event filtering and there's expression syntax. And a lot of what we're looking at today is kind of like similar to like the sysdig command line tool or for like strace. And you can see there's, you know, PID filtering, event triggers. You can do like very exciting like filter syntax and try to get specific things out of it. One of the things that is interesting is that the kernel is smart enough not to report data you're not looking for. Think about that. The kernel's not going to report data using these set of features that you're not looking for, because we understand how valuable our runtime resources are. And so if you go and you look at the eBPF subsystem, and if you look at U probes and K probes and everything, you'll quickly see that the whole fucking kernel is instrumented. We have it's like fucking spaghetti. It's like there's fucking functions on functions, and you can't even enter a function without calling a function to enter a function. And then you call the function to enter the function, and then that goes and kicks off another 10 nested functions that do all the instrumentation. And then you finally get back and you're like, I'm in a virtual function now. And then it's very abstract. It's very virtual. And it's just we've basically just said like everything we do in the kernel comes with like these predefined constraints, and that's where all of like the virtual memory management comes from, is by using like the internal kernel plumbing to do everything instead of actually just going and writing a regular boring old C function and calling a C function. You don't really actually get to call actual functions in the kernel very much. You're lucky if you do, and you're probably going to break something if you do. That's kind of been my experience anyway. So hopefully that helps answer the question. So anyway, back to what we're looking at. We're trying to find the accept queue. Now that y'all kind of understand what's going on in the kernel here. So what we want to do, there's a few things we can do. So we can try to just look through all events and grep for strings and keywords and see what we see. We can also try to guess and check, and we can also just go look at the kernel code and try to form a plan that way. I think my approach is I take a very like pragmatic observability approach to these things. I just want to see all the data, and then I just start looking at it and see if I see anything that looks familiar and work back from there. And that strategy is a pretty common strategy in like the observability discipline anyway, just to basically say like, just give me a bunch of data and then I'll start reasoning about it and seeing what like looks exciting and looks like it'll make sense to me. And so we can definitely do something like that today. And we can either do that with all of the events, or we can start with like specific system calls. So, you know, for example, one approach might be, because we know every time we call listen and we don't call accept, we have a record in the queue. We could just do like some quick arithmetic and, you know, listen +1 and accept +1, and then nobody's called accept, so we still have a record in the queue and we could count the queue that way. Another way would be we actually instrument the qlen field in the struct buffer struct, or in the socket buffer struct in the kernel somehow. And then a third way would be just to try to like look and see using native primitives what we would want to do. So let's keep looking and see what we come up with. we'll just start looking at events and see what we see. Let's just try to gain some basic footing. So this will be like when I say kernel hacking, this is what I mean. I don't know, I'm not a kernel expert. I don't know very much about the kernel, but we can go and try to figure it out. Okay, so we'll say echo 1 enable. Okay, and we'll cat this. And we will pipe to grep, and we will do grep minus I accept. And there you go. And so you can see here, we're getting some sys accept. Cool. So what we can do here is we will stop that curl, and we will stop that, and we're going to get our little like test bed together here. There's our curl. So we're going to, there's our server, there's our curl, there's our eBPF. Why do I have 4 open? I guess I have 2 roots. There's our accept, there's our curl. And here we go. This is what was wrong. This was my Linux one. So we'll go to source Snoop kit sudo e bash servers dysfunctional listen not accept TCP exec. So we will look for accept, and we will run our server here. I don't think we're going to see anything just because nothing actually calls accept, but we can try and see. So accept is not receiving. So we can also try to grep I. Let's go look at my blog really quick. Where's that GitHub? .NET MD here. Here's my blog. We can look for, what was the name of this function? Didn't I have kernel code in here? Here, request sock queue. So let's grab for sock maybe? I think sock seems reasonable. We'll probably see some socks show up. We'll probably see a lot in my, yeah. Let's see what we can ignore here. TCP probe. Address family inet. So we could grep for 9074. Let's just try 9074. Oof. There we go. So TCP probe looks to be our friend here. So this looks very similar to what you're going to see with TCP dump for obvious reasons. This looks very similar to what you're going to see with strace for obvious reasons. And what we're looking at here is, let's see if we can't find some valuable data. So it's the TCP probe trace point. We know that this is family AF inet. So this basically tells us we're using the Linux networking stack. AF stands for address family, and inet tells us that it's basically the inet section of the network stack. There's other sections as well, and each of these kind of like mean different things, but this is the main one. All of your TCP, curl, HTTP stuff, it's all going to be in the inet department. This source value here, the fact that we have this in the kernel, it just makes me so happy, but and we can easily print it out, makes me so happy. But basically this is just the source is coming from localhost on 9074, and our destination is going out to this ephemeral port here, 3292. Data link 0, we're not sending a payload, and send next, send UA, and these are all this is all of the TCP information that goes along with our request. And you can see here we have a socket cookie, which tells us we're using, if you see a TCP socket cookie, that tells you you're using the fast open TFO part of the kernel. So you know that this is, we're in the right part of the kernel we're trying to look into. This doesn't tell us how many is in the queue though. So this event is emitted from a server as the source is 9074. That's right, do Java. That's very right. That's very right. So this is emitted from the server. And so we're likely seeing this socket cookie correspond to, if you look here, there's this fast open queue. And if you go dig into this fast open here, this is a good little write-up on fast open. And you can see here, if we grab for cookies, maybe fast open connect. Let's go back. Let's go to this one here. Maybe it's here. There we go. There's a TCP cookie here, and this talks about fast open. So this PDF that we're looking at was written in 2011. There's some folks at Google who did it, and it basically just says, you know, what we're trying to build TFO for, and this is what later became the fast open stuff in the kernel. And one of the main reasons for it is because of this whole SYN flood problem here, which when I started my career back in the olden days, Chris Nova, SYN BSD GitHub, maybe. I thought I had like a, maybe we can find it. Spin spoof. Here you go. So this is gonna age me a little bit. I wrote this 7 years ago. Back in the olden days, these types of programs were a little more exciting than what we see now. But you could see here, you were basically able to do like a SYN flood against a server and send a bunch of SYN requests without a cookie, and and FreeBSD was notoriously bad about this at the time. But you were basically able to very quickly and very efficiently and effectively take down a server. And so Google, you know, in 2011, we're basically like, we're going to do some analysis with the TCP handshake, and we're going to introduce this TFO cookie, and we're going to go and we're going to make it to where like you can't really, we're not going to acknowledge and process these SYN requests unless you're kind of doing your fair share of work on your end as well, which is where these cookies come from. Those cookies are what we see right here. Okay, so we're looking at we're trying to find parts in the kernel where we might see this, oh, sorry, hold on. Where we might see this accept queue grow. And so we're looking at TCP probe, which could be one of them. Let's echo 0 to enable. So we know, let's take some notes actually. Where's my notes? We'll say TCP probe seems to be showing the sock cookie, and TCP meta information for the server. And then we'll just drop this in. Where was we'll drop this one in here. Cool. So let's now go and let's just start looking around. Let's go look in net. So we have net device queue. Who knows about Fentry Fix-It? Does anybody here know Fentry Fix-It? Does anybody here know Fentry Fix-It? Show of hands. Who here knows my homeboy Fentry? It's like Goose and Gorge. Do y'all know? Does anybody know Goose and Gorge? Does anybody? Any Bueller? Fueler? I'm not seeing anybody in chat. I live under a rock, apparently. No. Okay. Sentry. And Fexit. We have Fentry and we have Fexit. So Fentry is basically function entry, and Fexit is function exit. We have Fentry and we have Fexit. Goose. I was just trying to hope somebody had heard of weird parts of the code base being pronounced with funny names. Goose is Go operating system and Gorch is Go architecture. So we have Sentry, Fexit, Goose, and Gorch. These two don't have anything to do with each other other than the fact that they have silly names. But Sentry, Fexit is one method of instrumenting function calls in the kernel. So we could do Sentry, Fexit against like the specific C function we're trying to instrument, which would be, see if I can't get back there. I guess we go .NET MD here, which in our case would be something like this request sock queue, and there's some other places in the kernel source code we can look at in a moment to try to actually understand where to do it. Sorry, not in this function, but any of the functions that pass this around. So there's like a listen open, and there's like a fast open, and there's a few other functions in the socket code base we could instrument with Fentry and Fexit. Okay, aren't Fentry, Fexit used in a live kernel patching? I've heard about them. Yeah. So we used Fentry, Fexit in Boopkit. I think we did. Let's go see. Let's go see. Let's go to Boopkit. And Fentry. Maybe we didn't use Fentry, Fexit in Boopkit. I forget where I've used them before. I know I've used them before. Dan Kluver says, LOL, I was tabbed out, so I didn't know you were talking about Goose and Gorch. Never heard them pronounced that way before. Yeah, no, it's Goose and Gorch and Fentry and Fexit. Can confirm this with, like, Mastodon posts if required. Can confirm. So, anyway, we're getting sidetracked. Let's, eyes on the prize here. So let's look and see what we have here. So we have net dev queue. We have net interface receive socket buffer. I'm wondering what net dev queue. Will actually report. There we go. We could use perf for some of this stuff, but we're going to actually look at... I'm just reading some code here. Let's look at net dev queue. Let's just look at it. Okay, so net dev queue. Okay, so echo 1 to enable. And we run our cat command. And this time we can just turn off all of our grepping. And sorry, let's go to sys kernel tracing echo 0 to enable. Events. There we go. And then let's make sure this is, where are all of these coming from? CPU idle. NVIDIA. Call function entry. See, this is Fentry. Call function entry. Where, and here's Fexit. Function exit. Do we have syscalls enabled? Echo 0 to enable. At trace pipe. Echo 0 to, what did we say? Net. And then we said net dev queue. No, it's still on. What? How do you turn everything off is the question now without rebooting my computer? This terminal is so trippy. Something along the lines of find, name, enable, xargs, cat 0. Or cat 1, actually. Here. So I think I can do go 1 to how do I, but it's not redirected to the files. Hype says Edison pajamas. I also think that we want to, there's available events, kprobe events. Sorry. Let's go to events. This should work. For I and find, do echo. For F in do echo. Do 0 to I. Done. There you go. Okay, so F. There we go. There we go. And then cat trace pipe. There we go. Okay. So let's cat sys kernel. Thank you for helping me with that for loop. Tracing trace pipe. There we go. Okay, so now let's go to net dev q. Let's go try this one out. Echo 1 enable. I just like to call it enable, and then we'll run our cat. Okay. I'm not seeing much from our socket buffer adder, so we're getting the name of the process, so we can grep for actually, let's just do this. And where's our curl? Nothing. We want to run a successful server. Question is socket a device? Yeah, I don't think it is. I was mostly hoping that localhost was going to be a device and localhost was going to show up, if you know what I'm saying. And this is what I mean when I say we're digging into the networking stack, right? Like, there's what, 6 main layers of the Linux networking stack, from coming off the wire to Ethernet frame management to IP management to the routing layers to net filter to, I mean, there's just so much junk in there. But I mean, it all makes sense. But yeah, just getting a fucking connection up to user space is like a pretty non-trivial exercise, as it turns out. So let's turn this off. And let's just start ignoring some. So we'll grep v OBS. Okay? And we'll grep v SE. Okay, so now we have, and we'll grep v idle. Okay, and then we'll grep v chrome. Getting closer, and we'll grep v firebot. And we will grep v pool. And we will grep v capture, and we will grep v ksoft, and we will grep v cinnamon. Hey, there we go. So this is threaded ML, renderer, done server. That doesn't make me feel very good. Why is there a stun server on my computer? That's terrifying. Hold on. Did I get hacked? Stun WebRTC? There's Brave. Compiler. You got Discord open, maybe that. Yeah, it's probably Discord. Okay, so Brave, Zoom, so it's Zoom. Wow, today we're learning so much about our sockets that we have going on. So let's keep looking. So another thing we can do, let's do this. Turn this one off, and we'll echo 0 to, what was it? Net dev q enable. Okay. So let's go here. Let's do echo 1 enable. We'll turn everything on again, and we'll cat, and we'll get rid of all of these greps, and we'll just do a single grep dysfunctional. And actually we'll just do dysfun. There you go. Virtual runtime. Let's just see what else we can get. So we'll grep v runtime. Local entry timer, soft IRQ entry. Okay, so let's run a quick test. So let's... Dysfunctional listen. Is that still running? Let's see. PS aux grep this. It is. pkill f dysfunctional. Where was that running? Oh, it was running here. That's why. Okay. So let's... Sorry, I know I'm all over the place. Let's get my curl back. Alnova got our curl back. Curl localhost 9074, connection not accepted. Cool, listen not accept. And where's my grep? All right, let's do this. We'll go quick. Run the server. Send our curl. Close our server. Okay. I don't think we actually sent the curl though, is the problem. So dysfunctional listen not accept TCP. And oh well, I guess we would have needed to do this. There we go. So let's actually look through and see what we got. How much data did we get here? For IRC, no accept. Yeah, so we're seeing the loop is what we're seeing here. And so this is us getting up to the loop. Got it, yeah. So we could do a more efficient sleep. We could actually call pause, and that would be less obnoxious, but we can also do this. Let's get rid of the loop. So we can ignore schedule stat runtime. Okay. There we go. And let's write this to temp kernel trace.txt, and we'll actually do it to that temp. Okay. And 3, 2, 1, run the server, send a bad curl, stop the server, confirm the curl is closed, and kill our trace point. And now let's catch temp, what did we call it? Kernel trace less. Okay. Let's see what we have here. So we have HR timer start. So these are all the trace points. Remember I said earlier that the kernel is like instrumented well. A lot of these that we're seeing here is just the kernel plumbing, doing things like calling schedule wake up and actually executing processes. And there's a lot going on. Lots of timers, lots of messages, lots of queues. Okay. And syscalls should be in here. So we might even get lucky. We might even get to see a syscall in here at some point. Let's go up to the top and let's go down one page at a time. IRQ entry, RCU utilization. This is all of the perf stuff. IRQ raise. Work queue, activate work, timer expire, schedule waking. Soft IRQ. HR timer, local queue. x86 FPU, schedule wake up, work queue, activate work. HR timer. I'm not seeing really anything all too terribly exciting here. RCU read message. We're looking for like a listen, or I'll take a bind. Here we go, memory map. Okay, so now we're starting to allocate memory. So strings are getting managed now. Memory is getting allocated. That's what's happening in the context of our little server. We've created a user slice. So this is systemd doing what systemd does. These are like little slice C groups is how systemd likes to manage things. We have a flush on task switch. Let me zoom out just a little bit. There we go. Cool. So memory mac lock acquired. We're locking memory out of the kernel. And that's it. Signal deliver, sig9. So here's when I terminated the process. Did I just skip over a bunch? I feel like we lost a lot of... Maybe there's not much going on. Where's that memory allocation? Hey Corwin, welcome to the Nova Show. So RCU utilization, signal generate. In map is startup of the process, sig9 is the end, not much happening in between. Yeah. Lock acquired. This is where we terminated it, and this is mmap cleaning up the process. I'm not seeing anything in here. So the other thing we can do is we can check the listen system call. Let's talk through this really quick. I'm off to sleep. Have a great day, night. Yeah. So we can check the listen system call. Ooh, have a good night. Sorry, I had to sit down. I was standing up that whole time. But how do we want to... Let's look at the kernel. Let's look at the kernel code. What do y'all think? Okay, so here's the kernel code. So let's go to include net. And let's look at... Actually, let's open this up in C Lion. We're gonna open this up in C Lion. So open Linux. Here we go. This is gonna load 50 million fucking gigabytes of kernel stuff into my memory, and I'm okay with that. Net filter, net. That's net intel. We're in the wrong net. Where am I at? Include net. There we go. This looks right. Okay. So we have TCP con H inet IPv6. Where's inet connection 6? inet 6 connection sock. We want inet connection sock H. This is the file we want to start in. Okay. So many people see the TCP sources. This is the so what we're looking at is the internals of the Linux kernel where connections are established. So we opened up this inet connection sock.h, and this is just the header. This is none of the actual implementation detail. This is just the header. So here's a function called con request. We have rebuild header. We have send check. We have send receive sock, which this returns a sock. These are types, set sock option, inet connection oriented sock, pointers to address related TCP functions, i.e. things that depend on the address family. So these are the functions for address family operations. Send receive sock. This is part of the TCP handshake. Con request. This con request might be what we're looking for. Let's keep looking. inet connection sock. inet connection oriented socket. I check socket accept queue. FIFO of established children. This has got to be where we want to look. I sock. So we have this request sock queue, and for some reason it's not doing the thing where I can go and look this up. To search, press Control Alt 7 again. Control Alt F7 again to search in project file. Why can't I go and... And I think this IC accept queue, I think this is what I had in my blog. Let me go make sure. No, I had request sock queue, which is in request sock.h. Maybe this is where it's defined and I'll get lucky. So request sock. Send cookie. Here's request sock. It's like, why is there actual code in the header file? I don't know. The kernel is so fucking weird. Okay, here we go. For a TCP fast open listener, that sounds an awful lot like what we're listening for. Lock protects all access to the request socket, which is co-owned by the listener and the child socket. Makes sense. Q lane, pending TFO requests, still in TCP send receive. This is probably the most important thing we found today, is that line 142 right there. So we know TFO is the TCP fast opener. We know from our work in BoopKit that TCP send receive is an exciting TCP state that is established while we're waiting for somebody to call accept, which is exactly where we are today. So if we go and we look at a TCP handshake diagram, which we can find in the RFC, you know that state diagram, like the state diagram for TCP handshakes? It's in here somewhere. I've looked at this stupid fucking file enough. Here we go. Welcome to the state diagram from September of 1981. You guys ever seen the movie Hackers? You know, and they're like carry around that like TCP socket state diagram manual for 1981. Like they're not kidding. This is a 50-year-old fucking ASCII diagram, you guys. Okay. So we're in TCP send. What did we say? We're in TCP send receive. Activate, open, listen, receive, send. So closed, listen, passive, open, create, receive, send, listen, send. So we're in TCP send receive. So we're right here. So we've basically received the state and we haven't actually established. So where is accept? ACK the send. So I guess accept is what calls the syn ACK. I would love to see where glibc fits into this diagram. Anyway, I digress. I think we're here. I think we're right there. Pending TFO request, still in TCP send receive. I think accept is called by the process. The Crayola books. Not the TCP handshake. No, so in order for it to be in a... So basically it's... Accept passes off the connection pointer in the kernel. And then I think the accept function is the function that actually calls syn ACK on the inbound connection. Right? And that's why we see these like hanging socket states. I'm almost confident. We can write a little test to be sure, go look at the code, but I'm pretty confident that's how it works. I also know that there is a TCP handshake where we do like basically a syn ACK at the listen stage as well before we actually establish the connection. Which I think is denoted basically right here. Over here. So there's like two things that kind of happen at the same time. There's the receive send and the send send. Does that make sense? which is here. And then this path, we basically send a sent back to the client while we are in now send ACK established state. But I just don't think that we're actually going to send the send ACK packet or the header in the frame back to the client until we're at this established point here. And then we can transmit data, and then there's, you know, fin and wait and everything else. And then we can close, and there's all these like goofy, weird end states for obvious reasons. Anyway, I'm pretty confident we're right here. So, and we can go look and be sure. So, ideally these fields can be made as part of listen sock structure above, but there is some implementation difficulty due to the listen sock being part of the request sock queue, hence will be freed when a listener is stopped. But TFO relates fields and may continue to be accessed even after a listener is closed. So fast open queue for a TCP fast open listener. So to me, this basically says for every TCP fast open listener, which is how that's how we call listen in the kernel, basically, it's going to do a fast open queue struct. And this qlen is defined as the number of pending TCP send receive requests. This is the queue we're trying to find out. We basically want to get this integer out of the kernel. And this is a queue of request socks. And then basically this request sock queue is what we saw in, let me open it up, is what we see in, where was it? inet connection.h. Request socket queue. Okay. Request socket queue. Request sock queue. See, this string matches this string. Request sock queue. Okay. And then a fast open queue is just nested in this request sock queue. Y'all with me so far? So queue removed, and then I bet we have all of our queue methods down here. You know, you have qlen, request socket queue added, queue removed, and this just returns qlen. So I bet if we take this string and we copy, typically how big of a queue do you need? Personally, I only use 2 sockets at a time. So this isn't about queue size, it's about seeing when things queue. So this is 6.2. This is 6.3 release candidate 1. Request sock.h. Sorry, bad joke. Okay, typically how big of a queue? Oh, it's 2 socks at a time. Oh my god, did you make a sock joke? I was like, well, that's cool. You only run two socket servers on your computer. I run a little bit more. Sorry, I went rock climbing the other day, so I'm stretching my hands out right now. Give me a second. Okay. Okay, so this is what we want. So let's see if we can't eBPF instrument request sock qlen. So let's do an eBPF entry example. And then Jay said with Aya, your rusty eBPF companion. Section XDP. Return atomic read qlen. Let's actually do this. Let's see where in the network stack we're calling this function. Before we start going and writing eBPF, let's just go see. Also, I gotta take a break here in a second. So inet connection sock calls it, I bet we see it in inet 6 as well. Inet checksum socket, request qlen, request sock. Here we go. Inet, what is CSK? C socket? What file is this? Where are we? We're back in inet connection.h, aren't we? Yep. Good old I know. Connection sock. That's what it stands for. Okay. So where were we? Here it is. So static inline inet connection sock request sock qlen, and this basically return. We get the qlen atomically, and we I check sock accept q. Where's our accept q? There it is. FIFO of established children. So this is it. This is the accept queue. And we'll atomically read. Oh, did we get rated? Theo's here. What up, Theo? Theo, how are you doing? How was your T-Mux this morning? Welcome to the show, Theo. I don't know why my little sound didn't go off for you. I'm sorry. Usually we have like a sound that goes off. Welcome to the show. Welcome in, everyone. Welcome to the Nova Show. I'm your host, Chris Nova. Welcome to the show. Here at the Nova Show, we do what I want when I want because it's my fucking show. Welcome our main man, Theo, to the party. We love Theo. Theo's awesome. If y'all aren't following Theo, go drop him a follow. He is fucking cool. He has got a great stream, great sound quality. His sound quality is better than mine. And he is super smart, super kind, and just an overall chill, awesome person. And frankly, from the looks of it, if you're lucky, you get to see he's a kick-ass dad as well. And I'm just so happy to see really awesome people like Theo here on Twitch, and just feel lucky to call folks like Theo like one of my good internet homies that I have. I feel like we're like friends. We're like internet Twitch friends at this point. Like we've been raiding each other back and forth for like a year. So it's like, and like we watch each other's streams. So it's really cool to feel like our little Twitch community is growing. So Theo was working on T-Mux this morning, I think. As well as I think there was some hack the box in there. Were you able to get root on your server? Do you want to share which hack the box you were working on for folks here interested in cybersecurity? Cool. So really what we want to do is we want to know what is referencing this connection socket accept queue. So ACK, push, these are all the states. Transmit timer. Here we go. Destination entry. Sock. Request sock. INET. Request sock. Etc. Etc. Listen is a special case for pull. Accept queue. Here you go. This is exciting. So here's ePull, which we all know ePull is, that's basically how the kernel does, not concurrency necessarily, but it manages a lot of the strange, like, kernel eventing, and you can kind of think of it as like rudimentary IPC for the kernel. And so ePull is a big feature. In FreeBSD, we have KQ is what it's called, but it basically solves the same problem. It's just like this is what I meant earlier when I said kernel plumbing. If you're going to pull things in the kernel, there's like some guarantees that the kernel gives you, and it's like a Java monolith. Like you can't just like read a variable. You have to like establish the variable read factory and then call the variable read factory shared informer and then get the resource and then call set on the resource. Like it's like totally this fucking thing. Anyway, ePull is pretty much that, but in C for anything in the kernel that can happen. It's like concurrently, basically. TCP ping pong threshold, INET soccer, and INET sock. It's a great file. So let's see. Let's go back up. So we have an INET connection sock. So what we want to do is we want to figure out which function calls in the kernel create a new INET. Let's write this down. Let's write this down. To do. Figure out which functions in socket.h create new instances and instrument them. Okay? And instrument them. Surface. Let's actually go and look at this really quick before I keep moving forward. So we'll say sock dot. Is it sock.h? It's socket.h, I thought. Thank you all. Is it INET common? INET sock.h? Maybe it's this one? Well, these are just the headers. I think we need to go into the user API and actually look for the code. IP options, INET request sock. So this is higher level. So let's go to Linux net. Is there a user API? Socket.c, syscontrolnet.c. TLS Unix. Net. IPv4, IPv6. Hardware, Bluetooth, BPF filter, net filter, ARP. Here we go, we're getting closer. ICMP, we're getting closer. INET connection dot C. We found it. grep for INET connection socket. There you go. Sock.h, here we go. Wait for an incoming connection. Avoid race conditions. This must be called with the socket locked. I think we found where we're going to instrument the kernel, you guys. Finally, it's taken what, 2 hours, 3 hours?
true wake one mechanism for incoming connections. Only one process gets woken up, not the whole herd. Since we do not race and pull for established sockets anymore, the common case will execute the loop only once. Subtle issue, add wait queue exclusive will be added after. And here we go. Prepare to wait, release sock, request queue empty, schedule annotate sleep, lock socket, request queue empty, accept queues, break. What is this called? inet wait for connection. So this is in which file? inet connection sock.c. Net. Let's see. Hold on one second. Net. We said IPv4, right? Where was it? HIPv4 inet connection sock.c. inet connection sock.c. And we grepped for inet connection sock, and there it is. And let's go back to my Emacs Surface. All new IPv4, IPv6, UDP, and Unix domain socket connections. Q lens. Example for IPv4, and there we go. And this is what we want to instrument. And we can grab for a herd. There it is. Socket sleep, wait. So really what we're gonna want to do is whenever maybe we instrument one of these lower level functions, but whenever this gets greater than like some value, we want to just send data to user space. We'll figure out the implementation detail later. I gotta go take a break and cook my family lunch. I'm fucking out of here, you guys. I'm done. Fuck Twitch. I hate Twitch. I'm never twitching ever again. I'm just kidding. I love Twitch. I love you all. I'm gonna miss you. Thanks for sticking around today. I'm your host, Chris Nova. Welcome to the Nova Show. Follow me on Mastodon. Come hang out with us in Discord. Donate to our nonprofit if you can. We host a Mastodon server and we like the money. It helps us. So if you get time to donate to the nonprofit, please do. You can run the donate command in the chat if you're interested. You can go to nivenly.org. I'm on Mastodon, hackaderm.io/@Nova, N-O-V-A, my last name. I love you all. I will be back doing more eBPF. I'll actually probably write some code now that I know what we need to do later today. So stick around, smash that follow on Twitch if you haven't already. Tell your friends how good of a time you had hanging out with me on Twitch because you like it here and you think it's fun. Tell your mom you love them, tell your dad you love them. Be nice to your neighbors, love each other. You're doing great, hang in there. If you're impacted by the Silicon Valley Bank situation, it's gonna be okay. This has happened before. You're gonna get your money. You're not gonna get into a situation where things are gonna become catastrophic. It's gonna be okay. You can even use these FDIC filings if you want to talk to your landlord. You can use them to talk to your employer, to HR. There's a lot you can do. There are plenty of options out there. You just gotta go find them. So don't let it get too much to your head. You're all going to be okay. That's going to be okay. All of my investments, every fucking investment I've made to Silicon Valley Bank, I have no idea when it could be gone forever. I have no idea. I'm in the same situation, except for I am fortunate enough to be on the investor side of things, which that's a different discussion for a different day. Anyway, I love you all. I think you're wonderful. Who do we want to raid? We can raid MT Taggart, who's a cybersecurity person. We can go watch the Space Vixen play Mario. We can go see Lana work on her video game. We can go see Rob do some weird, who knows what Rob is doing. He can be doing whatever he wants. We could see Algo Bro. We could see Acorn. Thank you, Gannett, for the book link. That's amazing. Big Gem says, no, I love you more. Thanks, Big Gem. What do y'all think? Lana or MT? Let's go with MT Taggart. We're gonna go with Taggart. Y'all need to go. We're gonna go with MT Taggart. MT Taggart. We're gonna go with Taggart. Decision made. All right. I'm out of here. We're gonna go do some security work. I love you all. I think you're great. We'll see you next time. Peace. Thanks for the stream, Nova. Have a great day. Yeah, thanks everyone for sticking around. I'll see you next time. I'm out of here. I love you all.